Greetings. We will continue our discussion on the degeneracy of the hydrogen atom, and essentially the question that we have raised is, why is it that the 3p energy of sodium is different from the 3s, whereas in the hydrogen atom there is a degeneracy. Both of these 3p and 3s belong to the same eigenvalue. Okay, so this is the main question that we have been addressing. We have set the context of our solution to this problem, which is going to be a quantum treatment of the Laplace-Runge vector, which I discussed briefly and which you have studied in your classical mechanics course. This is an additional quantity which is conserved for the 1/r potential. It is conserved strictly for the 1/r potential, and the potential must be 1/r for the entire domain of space from r going from 0 through infinity. Okay, that is a requirement. In the sodium atom, the potential is 1/r for the outermost electron only in the asymptotic region as r tends to infinity, but as r tends to 0, the potential goes as minus z/r, where z is the number of protons in the nucleus. So it is minus 1/r as r tends to infinity, but minus 11/r as r tends to 0. So it is not on top of 1/r in the entire domain of space. So that is the difficulty with the potential for the hydrogen atom, that it is 1/r over entire region of space, and for this 1/r potential there are some very peculiar consequences. Like in classical mechanics, the Laplace vector is conserved. You have this ellipse motion for the classical 1/r potential Kepler problem, and the ellipse does not precess. There is no rosette motion, something like what would look like the petals of a rose from a distance. If this ellipse were to precess, it would look like the petals of a rose, and this is what does not happen for the hydrogen atom or for the classical two-body Kepler problem. However, the hydrogen atom is a quantum system. In fact, all systems in nature are essentially quantum systems, including the astronomical huge objects, including the planetary system, the galaxies and everything, but that is a separate issue. Now over here you must quantize the Laplace-Runge vector, and this is how you quantize it. You have to symmetrize the operator, because p and l do not commute, they correspond to measurements which are not compatible with each other, and therefore you have to symmetrize this operator. So this is the quantum Pauli-Lenz vector as we call it, and this is the classical two-body problem. And remember that, okay, you can use SI units. Now we are not dealing with the gravitational 1/r potential, but the electromagnetic 1/r potential, which is the Coulomb potential, and the corresponding force is 1/r square, but in SI system of units you have got this 1/4 pi epsilon 0, whereas in Gaussian you do not have it, and one has to keep track of these details depending on which system of units you are using. So we will use the Gaussian system of units, in which the proportionality will be E square for the electromagnetic 1/r potential. Okay, so we are going to use kappa equal to E square at a later point in our analysis, so remember that. Now we have done the symmetrization of this operator, so we have a quantum Pauli-Lenz operator now, and you must always keep track of what dimensions are appropriate for kappa or for the vector Pauli-Lenz vector itself, and you will immediately notice that these dimensions are ml3, ml to the 3, t to the minus 2, which are in fact, this is coming from the product of the dimension of the angular momentum multiplied by the dimension of the linear momentum per unit mass. Okay, that is because we introduced this specific angular momentum, right, which was the angular momentum per unit mass. So m into v would be the linear momentum, but you can also define the Laplace-Runge vector, and some books define it as what we have on the screen multiplied by the mass, and the whole thing just gets scaled by that factor, but the dimensions also go up by a factor of m to the 1. So you all must keep track of that, because you will see different things in different books. So it is basically the product of the angular momentum multiplied by linear momentum or linear momentum per unit mass, depending on which text you are following. We ask the question, if the components of the angular momentum and the components of the Pauli lens operator, do they constitute a closed algebra? So if you take the commutator of components of the angular momentum, then the commutator of any two is written in terms of the third component. So the algebra is closed within the components of the angular momentum. If you take the commutator of a component of angular momentum L and construct the commutator with component of the Pauli lens vector operator, then the answer is in terms of the component of the Pauli lens operator. So once again, there is a suggestion that you get a closed algebra between these two sets of operators. However, if you construct the commutator of these two components of the Pauli lens vector operator, the answer is in terms of the angular momentum, which is fine with us insofar as the closure of this algebra is concerned, but that is not the only operator which you get on the right hand side. You also get the Hamiltonian, okay, and this is an extra creature which pops up on the right hand side, which means that the algebra is really not closed. However, what you can do is to work in a subspace of the Hilbert space belonging to a particular energy value. You take one of the bound state energies, okay, and work within this subspace. The bound state energies have energies less than 0, that is the E less than 0 what is being referred to over here, and within this subspace then H operating on any vector in this subspace will give you the corresponding energy, which will just be a number, okay, it will be just a number with in so many electron volts or joules or whatever energy unit you are using, it will just be a number, and within this subspace you have a closed algebra which is generated by these 6 components, which then constitute the Lie group of dimension 6. So this is the SO4 group. The number of components SOn in any n is given by n into n minus 1 by 2. So for n equal to 4, you have 4 into 3 by 2, which is 6, and the 6 generators of this group SO4 are the 3 components of the angular momentum and the 3 components of the Pauli lens vector operator, and these 6 generate the SO4 group. What it means is that in this subspace, if you have any operator A, this script A, any operator which is a combination of angular momentum and Pauli lens operator, then if this operator operates on any function in this subspace, the result G will also belong to the same subspace. That is what essentially it means when we say that, okay, we are working within a certain subspace of the Hilbert space. So you confine yourself to that limited portion of the Hilbert space, which is a finite extract. You scoop out that part of the Hilbert space in which all the energies belong to a particular bound state energy E less than 0, okay, and within this subspace you have got a closed algebra generated by these 6 generators of the SO4 group, and within this subspace you can then work out these details, and these are left as homework exercises in your problem set number 1. You will find that these 2 operators are orthogonal to each other. You will also find that if you take the scalar product A dot A, the result will turn out to be this 2h over mu L square plus h cross square plus kappa square. I had referred to this result earlier, that this is something that will be anticipated. This is a there is this extra term h cross square which is coming, which you did not see for the classical Laplace Runge vector. This comes from the fact that the quantum operators do not commute. So you just make use of the commutation rules and you will get this quite easily. So this is what we have now, and we are working within this subspace of the Hilbert space. It is also useful to define another operator A prime instead of A, and there is no big new physics which is being introduced over here. This is just a multiplier, for introduced for scaling, and you will find that this makes our relationships somewhat easy to write and also easy to interpret. So you will find, so we will also be using this operator A prime, but there is no new dynamics which is being introduced over here. We will also make use of natural indexing. So instead of calling the components as Lx, Ly, Lz and Ax, Ay, Az, or A prime x, A prime y and A prime z, we will index them by these subscripts. That is just a matter of bookkeeping and convenience, and we will work with the 6 components as generators of SO4. Now it turns out that all of these operators which are 4 by 4 orthonormal matrices, they all have determinants +1 and they constitute a group which is known as the homogeneous Lorentz group. So this is the name of the group in this context of the hydrogen atom symmetry. You will remember that the rank of SO3 group, SO3 is the group that we assign to the symmetry of the hydrogen atom based on our simplistic analysis, in which all we made use of was the rotational symmetry of the potential 1/r, right. So you had angular momentum as generator of rotations, and from the 3 components you had the SO3 symmetry. None of these 2 components commute with each other because Jx does not commute with Jy, and no 2 components commute. So the maximum number of mutually commuting operators for SO3 is 1, and that in fact is the Casimir rank, that is the largest number of commuting generators, and the rank of SO3 is 1. So the Casimir operator for SO3 is J square. There is only one Casimir. J square is the only operator which commutes with all the 3 generators, which is the definition of a Casimir operator. By Raka's theorem, it is equal to the rank of the group. The rank of this group is 1. So there is only one Casimir, and this Casimir for SO3 is J square, and the question we are now going to ask is, what are the Casimir operators for SO4? Now that we know that the symmetry of the hydrogen atom we expect to be completely defined in terms of SO4 rather than SO3, we are going to now look for the Casimir operator for the SO4. So let us ask this question, what are the Casimir operators for SO4? So we will construct them now. What we will do, is to discover that SO4 has got a rank 2, and there are 2 Casimir operators. You will see what these are, and to get these 2 Casimir operators I define 2 auxiliary operators I and k. These are just the sum and the difference of the angular momentum and the Pauli length vector, okay. L plus A prime by 2, L minus A prime by 2. So this is just the half the sum and the difference. These are not the Casimir operators, but the Casimir operators are defined in terms of I and k. So to define I and k, I have introduced these 2 operators I and k as intermediate auxiliary operators, and the Casimir operators are defined as I square plus k square gives you one Casimir operator, and I square minus k square gives you the other Casimir operator. Now how do we know these are Casimir operators? Let us check it out. It also turns out that I square minus k square, and all you have to do is to literally do this term by term, and there is a fairly lengthy algebra in which most of us make careless mistakes, which makes that already lengthy algebra lengthier, and it can get to be very frustrating. But please spend all these hours, because you have to work out these commutation relations yourself. You are going to be tested for that, okay? And they are all based, you can all do that because they are all based on very simple commutation between position and momentum, which all of you have been using this basic commutator for quite some time now. So there is nothing new in it. So all you have to do is to use the basic commutation relations very carefully, and these results will pop out of that very easily. So I square minus k square, you will find, is exactly equal to the scalar product of L with A prime, which you know vanishes. And this is a very important result, because then you know that I square eigenvalues and k square eigenvalues will be equal, because I square minus k square has to identically vanish. So if it has to identically vanish, then the corresponding eigenvalues of I square and k square must be necessarily equal, and we are going to use that. How do we know these are Casimir operators? Well, check out what is the criterion of a Casimir. It must component with every generator. Okay, that is the definition of a Casimir operator. Casimir operator is one which commutes with every generator of that group. Okay, so find the commutation of the first Casimir operator, which is C1, with each component of the angular momentum. Do the same with each component of the Pauli Lenz vector operator, and you will discover that it does actually commute. So you convince yourself thereby that C1 is a Casimir operator. Do the same with C2. For every I, you will find that C2 also commutes with all the 6 components, and that pretty much settles the issue that C1 and C2 are Casimir operators. Now furthermore, if you work out the commutation between two components of I, take the commutation of Ix with Iy. How will you do that? When you take the commutation of Ix with Iy, you will take the x component of this, commute it with the y component, and then you will need the commutation between L and A. Okay, you know what those commutation relations are, we have introduced them already, use them carefully step by step. Okay, tiresome algebra, that is not something that we want to spend our time in the class, because it is lengthy algebra, but it is good work for you to do it at home. Okay, so work out this, any physics related problem we can discuss over here, but there is no need to spell out all the detailed steps and spend hours doing this algebra, which you can each do simply based on the basic commutation rules. So when you take the commutation of Ix with Iy, the result is Ih cross Iz, and have you not seen this result earlier? What does it suggest to you? It reads like angular momentum, does it not? Right? It reads like angular momentum. So you are going to begin to suspect that the auxiliary operator that you introduced, I, is an angular momentum operator. Same thing with K. K is also angular momentum operator. Okay, so in other words, the auxiliary operators I and K that we have introduced are angular momentum operators. They will generate the O3 as any angular momentum does. Okay, you will also find that the operators I and K commute, which means that they are completely independent. Okay, so there are two different operators I and K, they are completely independent, both are like angular momentum. You will also find that they commute with the Hamiltonian, which is a nice thing to do, because we have to be sure that we are working with operators which will operate on any function belonging to the subspace of the Hilbert space belonging to a particular bound state energy, and you want to stay within that subspace because that is what we have decided to work with, okay, so that we have closure. So each of the operators I and k, they constitute the O3 algebra, which means that they will have eigenvalue equations like angular momentum. So I square operating on a vector will give you an eigenvalue which we know from angular momentum algebra is h cross square I into I plus 1. We already know that from our angular momentum quantum mechanics, right. This is not a new result for us. Having established that I and k are angular momentum, these results automatically come because these come along with the definition or the defining criterion of an angular momentum. So all of these are natural, ingredients of the properties of angular momentum. So you can put a label, we know how to put a label in a state vector. So we use the label I to designate the state vector. We do the same with the k square, and this is the summary of the whole picture that we have got. Okay. So we began with the classical Laplace vector. We reminded ourselves of what consequences it has on the classical two body problem. We found that strictly for a 1 over r potential it gives you an additional constant of motion. So there is an additional conservation principle for which you look for an associated symmetry, and this symmetry for the classical problem is called as the dynamical symmetry because it comes from the nature of the force, which must be a 1 over r square. That is the necessary and sufficient condition for the conservation of the constancy of the ellipse, so that this ellipse does not precess. For the Bohr problem, for the hydrogen atom quantum problem, you again have a 1 over r potential. So we have exactly the same form of the potential, you have got the same kind of dynamics, but when you quantize the system, and we agreed that quantization does not necessarily mean that you have discrete energies or anything like that, it is one of the consequences, but the signature of quantum mechanics is that you must replace the classical dynamical variables with quantum operators. So you quantize the classical Laplace vector operator, but you can't do it by simply replacing p and l by corresponding operators. The reason is you do not get a Hermitian operator from that, and the reason it does not happen is because p and l do not commute, they are not compatible observables. So you symmetrize it, and this is a prescription for quantization, that you must symmetrize the operator. You get the corresponding operator which is known as the Pauli Lenz operator, and you find that you can define a closed algebra between angular momentum and Pauli Lenz operators, but only if you restrict yourself to a subspace that you must scoop out of the entire Hilbert space, a subspace which belongs to a certain bound state energy, and within that bound state energy you have got closed algebra. You introduce the Casimir operators C1 and C2 in terms of I and k, which are intermediate auxiliary operators which we now recognize as angular momentum operators, but not quite. These are called as pseudo angular momentum operators rather than angular momentum operators. Okay. Why pseudo angular momentum? They are not exactly angular momentum. They are angular momentum operators because they have the same algebra, but they are not exactly the same because there is still a certain difference. What is the difference? The difference is the following, that I and k are made up of a mix of these two operators L and A, right. You must superpose L on A, L plus A prime and L minus A prime or A, you know what the relationship is, that is just a multiplier. so do not worry about that. But you are doing an addition of angular momentum with the lens vector or the Laplace lens vector. Now, the Laplace lens vector is a polar vector, angular momentum is an eggshell vector. Okay? One is a vector, the other is a pseudo vector. So, when you take a sum of the two, the result is neither a polar vector nor an eggshell vector. So, it has got some attributes similar to angular momentum, but it is not exactly the same. And to highlight the fact that this is not a pseudo vector like the usual angular momentum vector is, you call it as a pseudo angular momentum operator. So, we have now introduced I and k, which are pseudo angular momentum operators, but they do satisfy the entire algebra of the angular momentum. They are generators of O3, and now we will do a little bit of mathematical very simple straightforward juggling with these operators, and we will find some very fascinating answers about our fundamental question of the hydrogen atom degeneracy come out of it. It is very simple, it is stunningly simple. Okay, we have also found that since I square and k square must be equal, because I square minus k square goes to 0, right, the eigenvalue of C1 will be twice the eigenvalue of k square or twice the eigenvalue of C1, right. So, the eigenvalue which I have written as lowercase c1 of the operator which is written as uppercase c1, the eigenvalue is twice the eigenvalue of I square or twice the eigenvalue of k square. They are both equal, so it does not matter whether you use I or k, because I must be equal to k, and this is the eigenvalue of the Casimir C1. Okay. You can also get this eigenvalue by working out the square of I and the square of k, and then getting the eigenvalue of whatever turns out to be from the right hand side. So, you can do it explicitly term by term. Okay. So, what is I square? Since I is half of L plus A prime, you take the square of it. You have to be careful because L does not commute with A prime. So, you have to write L dot A prime and A dot L separately. It is not twice one of the two terms. Okay. You have to write them separately. Same thing with I square minus k square. So, you have L dot A prime and A dot L A prime dot L over here with negative sign over here. So, you take I square plus k square, work it out. Now, this L dot A prime term with a plus sign will cancel this L dot A prime term with a minus sign. Likewise, this A dot A prime dot L will cancel this A prime dot L, and then you get half of L square plus A prime square, because you get two identical terms, and A prime square is in terms of A dot A. This is how A prime was defined in terms of A by an appropriate scaling. Okay. The square root of minus sign, let it not worry you, because the energy in the denominator is intrinsically negative. We are working in the bound state part of the hydrogen atom spectrum. So, these bound state energies are intrinsically negative, right. So, you are going to have square root of a positive number. Okay. So, you are not going to have the imaginary square root of minus 1 anywhere. And what you find is that to get the eigenvalue of this operator Casimir C1, you must find the eigenvalue of A dot A, which defines through the scaling mu over 2e what this A prime square is, and this A prime square appears explicitly in C1. So, let us get eigenvalue of A dot A. So, one expression for C1 we already obtained earlier, which was twice of h cross square I into I plus 1 or k into k plus 1s, and then we get another expression for C1 by constructing the eigenvalue of this right hand side over here. But for that we should also get the eigenvalue of A dot A. Once we do that, we will get two equivalent expressions for eigenvalues of C1, which you can then equate to each other, and that will almost be the solution to our problem. So, we are going to use this result very soon. Now, again a little bit of work and patience is required to show this equivalent form, which is left as homework exercise. You have already defined the Pauli-Lenz vector operator. You can write it equivalently in another form, which I have now written at the top of this slide, and using this form you can get A dot A term by term. Again, take the dot product of this term with itself, then the dot product of this with the second term, and then the reverse dot products. Okay. So, you just have to work out these terms step by step. What you find that as a result of this, you will have another form of A dot A, which has a term in h cross square which distinguishes it from the classical A dot A. In the classical A dot A you do not have this h cross square term, but now you have it, and this is coming simply because now you are working with quantum operators which do not commute. So, you have the Casimir operator C1, and for A dot A, which is this A square, we have now written this explicit expression which you find in this beautiful bracket, right, which means that the eigenvalue of C1 can be extracted from the eigenvalue of L square. You know what the eigenvalue of L square is? It is h cross square into L plus 1, right. It can be obtained from the eigenvalue of these operators over here. Kappa square is just kappa square times the unit operator. So, you know that the value is just the kappa square. You know kappa is equal to E square in our analysis. Okay, I mentioned that at the beginning of this class. So, you know that h cross square is known. Mu over 2E is going to multiply this 2h over mu. So, the mu will cancel. H in the subspace is just a number which is equal to E. So, whenever you have h in the numerator and E in the denominator, they cancel each other. They are exactly equal because h is no longer an operator so far as the subspace of the Hilbert space that we are working with. It is going to operate on any vector in that space and give you the corresponding eigenvalue, which is one of the bound state energies, which is E. So, it will cancel, and now you can simplify this algebra and you have a very simple result. You have got half L square, then you have got minus half L square. There is this half over here, this minus mu over 2E cancels 2h over mu, and then you have this L square sticking in. So, you have half L square minus half L square, and from the remaining two terms you have minus half h cross square and minus half mu over 2E kappa square, right. It is very simple, and this is really amazing because now the half L squares cancel. You have got the eigenvalue C1, but you also had an expression for C1 earlier, right, and now you can equate these two. They must be equal, they must be exactly equal. So, I have just rewritten these two terms with the second term first and the first term second. Sometimes I do these things just to confuse you, but it is the same, right. So, do not worry too much about it. So, you have got C1, this is the eigenvalue which we got earlier to be twice I into I plus 1 times h cross square, right, and now we get another result which is in terms of this mu kappa square over 4e minus half h cross square. Now if you forget this middle thing, you have got what is on the extreme left to be equal to what is on the extreme right. What does it tell you? It is giving you the energy of the hydrogen atom. It is giving you the energy of the hydrogen atom in terms of I. Here is a relation between I, which you know is an angular momentum eigenvalue. You know it is either 0 or half or 1 or 3/2 or 2, right. This is coming from the eigenvalue of the operator I, which is an angular momentum operator. It can have eigenvalues which are either 0, half, 1, 3/2, 2, etc. So you have got this relationship and you write it for the energy, and you get energy to be equal to 1 over n square, where n is 2i plus 1. Now this is an incredible result. We saw this result 1 over n square in the Rydberg-Balmer formula. It was first obtained empirically by Balmer and then by Rydberg. This was semi-empirical formula. Then we got it from the Bohr model of the hydrogen atom, which was introduced in 1913 based on a certain set of postulates of quantization of angular momentum of these Kepler like orbits. But we wanted to dispense with that model because there are no orbits in quantum mechanics. So the Bohr formula is something that we call as the old quantum theory. We dispense with that, although it gives the correct 1 over n square result. The model itself is not quite correct. It is like getting a good answer, a correct answer using a wrong reasoning. Okay, like you can divide 64 by 16 and cancel 6 in the numerator and the denominator and get the answer 4. Answer is correct, but the reasoning is stupid, right. So there are no orbits in quantum mechanics, so you can't really be using the Bohr model of the hydrogen atom because you cannot really have an orbit. The idea of an orbit is not compatible with the fact that position and momentum are not simultaneously measurable. So then you introduce the Schrodinger equation or the Heisenberg uncertainty principle, and you know that Heisenberg form of quantum mechanics is completely equivalent to the Schrodinger form of quantum mechanics, and using one or the other you can solve the problem of the hydrogen atom. Let us take the hydrogen atom, the Schrodinger equation for the hydrogen atom if you like, separate the radial part, the angular part, get the spherical harmonics from the angular part, put the boundary conditions on the radial part, and the answer turns out to be 1 over n square. Okay. Now we have got 1 over n square, but we did not use any semi-empirical relationship, we did not use the Bohr model, and we did not use the Schrodinger equation either, did we? We did not solve h psi equal to E psi anywhere. What did we do? We began with the Pauli Lenz vector. Okay, we fiddled with the properties of the Pauli Lenz quantum vector operator, recognized its properties, introduced the Casimir operators, did a little bit of algebra, found out what are the eigenvalues of the Casimir operators C1 and C2, and by simply doing this algebra we get the 1 over n square formula of the hydrogen atom. And I will like you to ponder over this question and ask yourself that, okay, without using the Schrodinger equation, without using the Bohr model, how is it that you get the correct quantum answer, that the energy levels of the hydrogen atom are given by 1 over n square? We have already discussed the answer, but I want it to come out to the top of your mind very clearly, because when you do that you will understand precisely what is meant by quantization. So just give it a thought, but we are of course going to discuss that. So this is the 1 over n square formula. There is something more to it, because n in this case is an integer, I can take values 0, half, etc. You know that from properties of angular momentum algebra. So if you define now an integer, I is either half odd integer or integer, so 2i plus 1 will always be an integer. For I equal to 0, half, and so on, the corresponding values of n will be 1, 2, 3, 4 and so on. So these are the natural integers that you will get, right. These are what you call as the principal quantum number for the hydrogen atom. But what is more is the fact that since I and k are angular momentum operators, they have a degeneracy which is 2k plus 1 fold, right. So there is a 2i plus 1 fold degeneracy for I and a 2k plus 1 fold degeneracy for k, but I is equal to k, so the degeneracy is actually 2k plus 1 times 2k plus 1, and 2k plus 1 is now an integer which is n, so you have n square fold degeneracy. This was our question. Why is it that the hydrogen atom eigenfunctions are degenerate? Why is the energy of 3p equal to the energy of 3s for the hydrogen atom, whereas for the sodium atom it is not the case? Now for the sodium atom we know it is not the case because the potential is not 1 over r over the entire space 0 through infinity. It is 1 over r only as r tends to infinity, but not as r tends to 0. As r tends to 0, the sodium atom potential, or for any other atom, it will go as minus z over r, whereas as r tends to infinity the potential will go as minus 1 over r. So it is hydrogen like but still different. And for the sodium atom you do have rotational symmetry, and then you get the radial function for the sodium atom if you set up. Then you already know that for bound state energies, for the discrete part of the spectrum, no energy value is degenerate in one dimensional problem. Now that result is quite consistent and happily satisfied by the sodium atom, but it is not satisfied by the hydrogen atom, and it is for this reason that the symmetry of the hydrogen atom is something that you would have called as accidental symmetry, but only as long as you did not understand what is it that caused that accident. Now we do not have to call it as an accidental symmetry anymore, we know precisely what it is. The symmetry is SO4 and not SO3. Because the symmetry is SO4, there is an additional symmetry coming in. This additional symmetry is a special feature of the 1 over r potential. The situation is quite similar to the classical problem. There is an analog in classical mechanics, because by studying the properties of the Laplace Runge vector you can get the equation to the orbit without actually solving an equation of motion. That is the analog over here. So now let us look at this degeneracy. So I can take these values 0, half, 1, 3 half, 2 etc. Correspondingly 2i will be twice this, and n which is 2i plus 1 will be these integers 1, 2, 3, 4, 5 etc., and the degeneracy will be n square, and this is precisely the degeneracy you find for the hydrogen atom. You do know that this degeneracy then gets multiplied by another factor of 2 because of spin. So that will come from relativistic hydrogen atom when we do that. That is a topic for our unit 3, and we will see how spin enters quantum mechanics. So you get the Rydberg-Balmer-Bohr relationship. You are able to explain the degeneracy of the hydrogen atom now in terms of the SO4 symmetry, and that is where I will conclude today's class. I will be happy to take some questions, but now we fully understand that to get the yellow lines, D1, D2 lines of sodium atom, there has to be a transition from 3p to 3s. This would not happen if they were at the same energy, if these states were degenerate, right. So the D1 D2 lines come from the fact that 3p energy is different from 3s, which is what is expected from the radial equation that you get by separating the angular part from the radial part, right. You get a one dimensional problem and you have got a fundamental theorem in quantum mechanics that for discrete part of the spectrum you do not have any degeneracy, and that result is completely satisfied by the spectrum of the sodium atom. But the hydrogen atom, which is of course the simplest atom that one can think of, it would leave us with a problem which would make it look like an accident of nature, and it is only because we had not fully recognized the symmetry of the hydrogen atom. It is SO4, we get the Casimir operators, and from the properties of the Casimir operators we get the spectrum which is 1 over n square, but it also explains the degeneracy of the hydrogen atom. In our next class, which will be tomorrow, I will discuss the wave functions of the hydrogen atom, and this is again interesting because we got the eigenvalues of the hydrogen atom without solving the Schrodinger equation, right. We did not actually solve the differential equation anywhere. We will now get even the wave functions of the hydrogen atom without using the Schrodinger equation. Nothing wrong with the Schrodinger equation, it is great, it is at the heart of quantum mechanics, but there is something to quantum mechanics which is more than the Schrodinger equation, okay, and that is what we are trying to develop some comfort with. Questions? Yes, Vivek.
Initially we started with saying like there are 3 generators LIs and 3 AIs.
Yes.
So totally we had 6. And from there you wrote Casimir operators directly.
Right.
So after knowing these 6, how one directly goes to, I mean, is there any way where we can see, okay, this might be a Casimir operator for us to figure out?
Well, the way to do it is to figure out what would be the appropriate Casimir operator for that particular group. Essentially, the number of Casimir operators you can get is equal to the rank of the group, and this is a very famous theorem which was established by Raka. This is known as Raka's theorem. And the rank of this group for SO3 is 1, because no 2 generators commute with each other. Angular momentum in quantum mechanics we defined through the commutation relations, and none of these 2 generators commute with each other. Lx does not commute with Ly, Ly does not commute with Lz, and Lz does not commute with Lx. So there is only one Casimir, and Casimir also showed that you can always construct a bilinear combination of the generators. What is this bilinear combination for the Casimir for SO3? It is J square, because J square is a bilinear combination, it is equal to Jx square plus Jy square plus Jz square, right. So this J square is the Casimir for SO3. So for SO4 you have 6 generators. The rank of this group is 2, and you have to find what will be the Casimir operators. So there are various ways that people do to construct the Casimir operators. Essentially you can get this only from what you have. In fact, I gave an example when we introduced the original Laplace vector. I said that you often learn about the equation of motion, and then you also learn about the conservation principle, but can you get one from the other? The answer is yes, that if you begin with the equation of motion F equal to ma, right, and then you construct the cross product with the angular momentum or the specific angular momentum, what came out was a constancy, which was the Laplace-Runge vector. So by playing with the terms that you have, you get new physics, or you develop new insights. So the operators that we have to begin with are L and A, and there is only so much algebra that you can do with these two operators. And if you start juggling with these terms, it does not take too long to find that I square plus k square and I square minus k square will give you the Casimir. And you can very easily verify, well, very easily so far as the physics is concerned. When you actually sit down to do it, it does take a little while. It is laborious but not difficult. Any other question? If not, thank you all very much.